When we visualize the solar system, we usually picture a clock. Neat, concentric rings, predictable, static, a safe, two-dimensional map. But that stillness is an illusion. The solar system is not a map, and it is not flat. It is a violent gravitational sinkhole, a massive, inescapable depression in the fabric of space-time, bending everything within trillions of miles into its curve. You are not sitting stationary on a quiet world. You are suspended in a high-speed orbital tension. Every planet, moon, and asteroid is caught precisely in the mechanical razor's edge between falling into a nuclear furnace and being flung out into the freezing void. To understand how this dynamic architecture was achieved, you have to discard the idea of planets forming first. 4.6 billion years ago, there was no sun. There was only a molecular cloud, a freezing, formless nebula of hydrogen, helium, and the microscopic shrapnel of dead stars. Triggered by a pressure wave, this cloud collapsed under its own immense gravity. As it crushed inward, conservation of angular momentum forced it to spin. It flattened into an accretion disk, a violently rotating platter of raw material. At the dead center, gravity drove the pressure to a critical threshold, 10 million degrees Celsius. Hydrogen atoms were forced together so violently they fused into helium. A nuclear engine ignited. But the birth of the sun created an immediate, violent problem for the rest of the disk, a massive thermal gradient. The inner solar system became an oven. It was entirely too hot for volatile molecules like water or methane to survive as solids. They vaporized. Only the heaviest, most heat-resistant materials, iron, nickel, and silicates, could remain solid in this inner zone. The inner solar system isn't rocky by accident. It is the dense slag left behind, where nothing else could survive. These heavy fragments collided and fused over millions of years, carving out their orbital lanes. But simply forming a terrestrial planet did not guarantee its survival. The inner system is a brutal gauntlet governed by two strict filters: kinetic stability and geochemical equilibrium. Mercury was likely a victim of the kinetic filter. Current models suggest a catastrophic collision with another planetary embryo blasted away its lighter silicate mantle. So close to the sun's gravity and intense heat, those lighter elements could not reaccrete. It was left permanently scarred, an oversized iron core baking in the dark. Mars survived the era of impacts but failed the filter of scale. Because it was small, its internal core cooled too quickly. When the core solidified, the planetary magnetic field died. Without that invisible shield, the solar wind progressively stripped away its atmosphere, turning a wet world into a freeze-dried ghost town. Venus and Earth faced the second filter, atmospheric equilibrium. Venus possessed the mass, but its carbon cycle broke. A runaway greenhouse effect choked the planet in a thick carbon dioxide atmosphere, driving surface temperatures high enough to melt lead. Earth survived because of dynamic geology. Tectonic plates subduct carbon back into the mantle, acting as a planetary thermostat. It isn't a miraculous oasis. It is a system of continuous, active chemical regulation. But as you move outward, the physics of planetary construction fundamentally change. Between Mars and Jupiter, you cross the most critical boundary in the solar system, the frost line.
Out here, the solar radiation drops. The vacuum becomes freezing. Suddenly, water, methane, and ammonia do not vaporize. They condense into solid ice. Because ice was so abundant, the planetary embryos here could grow 10 to 20 times larger than Earth. And with that immense mass, came immense gravity. They grew so heavy, they triggered runaway accretion, violently pulling in the massive clouds of primordial hydrogen and helium gas before the solar wind could sweep it away. Jupiter didn't just become a gas giant. It became the architect of the solar system. Containing more than twice the mass of everything else combined, its gravity dictated the fate of the remaining debris. Deep inside its crushing atmosphere, the pressure is so extreme that hydrogen gas is compressed into a conductive liquid metal ocean. The structure of the outer system is not the result of planets peacefully growing in place. The solar system was deeply unstable. As Jupiter and Saturn established their massive orbits, they likely locked into a gravitational resonance. This shifting mass acted like a cosmic bulldozer, destabilizing the entire disk. Uranus and Neptune were likely flung outward during this migration, pushed into the sparse outer edges of the nebula where raw material was scarce. Their growth stalled. They didn't gather enough gas to become like Jupiter. They became ice giants. Beneath their thick atmospheres lies a slushy, super-pressurized mantle of water, ammonia, and methane. The pressure here is so intense that carbon atoms are violently ripped from methane molecules, crushed into diamonds, and slowly rain down toward their rocky cores. If you want to understand the true mechanics of this system, you must unlearn the idea that the Sun sits perfectly still while the planets orbit around it. In physics, a massive object does not simply pin smaller objects in place. Gravity is a mutual exchange. Planets do not orbit the geometric center of the Sun. Every object in the solar system orbits the barycenter, the collective center of mass. Because Jupiter is so incredibly massive, the balance point between the Sun and Jupiter often lies outside the Sun's surface. The Sun doesn't sit still. It physically wobbles, pulled in small, looping orbits by the gravity of its own planets. Furthermore, the solar system is not a stationary disk. The Sun is hurtling around the center of the Milky Way galaxy at 500,000 miles per hour. The planets are not being dragged behind it in a vortex. They share the exact same inertial frame, falling forward through the galaxy together, a single capsule of immense momentum. From the kinetic scars of Mercury to the diamond rain of Neptune, the solar system is not a collection of isolated worlds. It is a single, interconnected mechanism, a structure carved by thermal gradients, orbital migrations, and the ruthless physics of condensation. When you stand on Earth and look up at the sky, you are not standing on a permanent foundation. You are clinging to the surface of a thermodynamic survivor. Every second, this planet is attempting to fly off into the freezing void of interstellar space in a straight line. And every second, the immense gravity of a burning nuclear engine pulls it back. We are not resting. We are held perfectly inside a 4 billion-year-old collision between velocity and collapse. We've spent today exploring the violent machinery of our own solar system, where gravity and velocity are locked in a relentless 4 billion-year-old war. But if this single interconnected mechanism is just our local neighborhood, exactly how unimaginably massive is the cosmic ocean we are falling through? Subscribe to join us as we measure the true, staggering scale of the universe in the next video. And check out our shorts for daily, bite-sized deep dives into the cosmos's most curious questions.